Okay, so this video is going to cover the last two objectives from section 7.1. So we're going to talk about objectives 3 and objectives 4 in this video. So again, keep in mind from the last video, one of the most important things that we have to remember now is that anytime that you're talking about area, probability, or proportion, they all mean the same exact thing. So one more time, area equals proportion equals probability. All those words are interchangeable. So if you're looking for probability and you can't find the probability, but you found the area, guess what? You've actually found the probability. Again, they are all the same. So again, our 4 objectives overall were to use the uniform probability distribution and to graph a normal curve, which we talked about during that first video. And now for objective 3 and 4, which will be in this video, we're going to state the properties of the normal curve and explain the role of area in the normal density function. Okay, so objective 3 is to state the properties of the normal curve. Okay, again, we've been talking about the normal curve a lot, so most of this shouldn't be too outside of the realm of what you already know. Okay, normal density curve is always symmetric about the mean. Again, remember when you have your curve, that middle line there is always your mean, so it's symmetric about your mean. And again, because it's normal and it's symmetric, the mean, the median, and the mode are all equal. So that means that that curve has a single peak and its highest point occurs at x equals mu, or x equals the mean. So again, that's happening right there. That's your highest point. For number 3, it has inflection points at the mean minus 1 standard deviation and the mean, that should be plus 1 standard deviation. Hey, again, you don't need to know anything else about the inflection point besides that it happens right here, inflection point IP, and here, sorry, that's 1 standard deviation. Hey, and that is your other inflection point. That's all you need to know about it. Hey, and again, as we talked about in that last video now, the area underneath that curve is 1. Again, 100% of that area, 1. Okay, so the area under that curve is 1. Okay, the area under the curve to the right of the mean equals the area to the left of the mean as well. So if I take the area to the right, there, that's in red, that would be 1/2. Okay, a half of 1 is 1/2. And if I take the area to the left of the mean over here, that's also going to be 1/2. Again, a half of 1 is a half, or 0.5. Okay, and as x increases without bound, in other words, again, as x gets larger and larger, so as you move to the right on that graph, the graph approaches but never reaches the horizontal axis. As x decreases without bound, again, gets more and more negative, so the further you go to the left on the graph approaches but never reaches the horizontal axis again. Okay, and again, number 7 is something that we've spoken about already. The empirical rule, approximately 68% of the area under the normal curve is between x equals the mean minus 1 standard deviation and x equals the mean plus 1 standard deviation. Approximately 95% of the area between x equals the mean minus 2 standard deviations and x equals the mean plus 2 standard deviations, and then 99.7% of the area lies between x equals the mean minus 3 standard deviations and x equals the mean plus 3 standard deviations. So again, we've talked about this before, and you're going to see the picture as soon as I scroll down on the next slide of that picture again. So there's your normal distribution curve, and again, you have your mean in the middle, and as you're going to the right, you're adding a standard deviation each time, and as you're going to the left, you're adding a standard deviation each time. Again, on the last slide, we said that 68% lie within 1 standard deviation. And again, just keep in mind that if the entire thing from the left side of that purple arrow to the right side of that purple arrow is 68%, again, everything is symmetric, which means half of that 68% lies to the left of that mean, and half of that 68% or 34% lies to the right of that mean. And that's really, again, all that there is to know about objective number 3. So now we're going to look at that for objective number 4. So we're going to explain the role of area in the normal density function. So the data on the next slide represents the height in inches of random sample of 52-year-old males. We're going to draw a histogram of that data using a lower class limit of the first class that's equal to 31.5 and a class width of 1. Okay, and then eventually for part B, we're going to answer, do you think that the variable, the height of a 2-year-old male, is normally distributed? Okay, so again, on the next slide, the very first thing that you're going to see already printed on your paper is that lower class limit of 31.5. I filled in the rest of the table already just because I didn't want to take the time to do it during the video, but I do want to talk about it. Again, that came from what I just was reading on that last slide, lower class limit of 31.5. Again, they told you your class width was 1. Again, remember what the class width is. That does not mean that your first class is going from 31.5 to 32.5. That means when you subtract the lower limit of any 2 consecutive classes, that's 1. Which means if this is 31.5 and I add 1 to it, that's how I get that 32.5. Which then I just went back up to here and subtracted a tenth from that to get the 32.4. Again, if you add 1 to 32.5, you're going to get 33.5, which again means that this one has to end at 1/10 below that, so 33.4. And that's just how I went up each successive class until I got to my last class. So there's all my classes. Again, as you go through and you put your tallies in for your frequency, I would just cross out your numbers as you go along so it's easier to keep track of. Okay, and then again for your relative frequency, remember the relative frequency is your frequency divided by the total frequency. They told us in the slide above that there were 50 males, or again, if you add straight down your frequency column, you should get a total of 50 tallies there. So relative frequency, there was one person that was between 31.5 and 32.4. So that's how I got the 1 divided by 50. That comes out to 0.02. Next one, 3. Again, 3 divided by 50, 0.6. And again, I just didn't write out all the other ones. For 31.5, the one that I'm putting the purple star next to right now, that would be 6 divided by 50, so on and so forth. And that's how you get all of your relative frequencies there. Okay, so again, when you make a histogram of that data on that last slide, this is what it should look like. Again, across your bottom, you have your classes, and across your y-axis, you either have your relative frequency or your percent or your area. Again, all the same thing now. Again, take a second, make sure you have that graph done before you move on to the next slide. Okay, we have a normal density curve over the histogram. How does the area of the rectangle correspond to the height between 34.5 and 35.5 inches relate to the area under the curve between these two heights? So again, here's the height of that bar. The height of that bar is right here. It's 0.2. So there's the height of the bar. Okay, and now the area of that green rectangle, again, the area of the green rectangle between 34.5 and 35, remember area is length times width again, your length there again between 34.5 and 35.5 is 1. And your width would be the height of that bar, and again, the height of that bar is that 0.2. So the area under that curve is going to be 1 times 0.2, which is just 0.2 or 0.20 or 20%. So how are they related then? The height of that bar and the area are exactly the same. So they are the same. By the way, I don't think we answered part B of this other question. Part B, do you think that this is normally distributed? Again, if you look at the shape of this, since this shape is symmetric, yes, it is normally distributed, just so you know. Okay, so the area under a normal curve. Suppose that a random variable x is normally distributed with a mean of mu and a standard deviation of sigma. The area under the normal curve for any interval of values of the random variable x represents either, again, area, proportion, probability. It represents the proportion of the population with the characteristic described by the interval of values, or the probability that a randomly selected individual from the population will have the characteristic described by the interval of values. Again, area, proportion, probability all mean the same thing. So here's an example. The weights of giraffes are approximately normally distributed with a mean of 2,200 pounds and a standard deviation of 200 pounds. Draw a normal curve with the parameters labeled. Again, so we're just going to do the normal curve with mean in the middle, so on and so forth. And then we're going to shade the area under the normal curve to the left of 2,100 pounds. And then for part C, we're going to suppose that the area under the normal curve to the left of 2,100 pounds is 0.3085. And we're going to provide two interpretations of that result. So again, this is already drawn for you, but again, let's talk about it. So part A is to draw the normal curve. So really all I'm doing is going back to, sorry about the scroll here, but this, okay? I'm taking this and I'm drawing that. And again, notice I have the mean plus 1 standard deviation plus 2 standard deviations plus 3 standard deviations. So I'm going to go to the right 3 standard deviations and I'm going to do the same on the left. I'm going to go to the left 3 standard deviations. Okay, so again, I'm just draw a normal curve, best of my ability. Right down the middle, that's my mean. And again, my mean was 2,200 pounds. Okay, and then again, we're going to go 1, 2, 3 standard deviations to the right. So if I take that 2,200 and add 200, that's going to give me 2,400. Next one will be 2,600. Next one will be 2,800. Again, just keep adding 200. And we'll do the same thing on the other side, but instead of adding, this time we are subtracting. So this will be 2,000, this will be 1,800, and this will be 1,600. So that's part A. That is your normal curve with your parameters labeled. Again, for part B, again, excuse my scroll. For part B, you want to shade the area to the left of 2,100 pounds. Well, when I look at my curve that I just drew, 2,100 pounds isn't on there. But again, this is 2,000, that's 2,200, and everything is symmetrical. So halfway between 2,000 and 2,200 is going to be your 2,100 pounds. So that red line represents your 2,100 pounds, which I just kind of circled in that other thing there because I was running out of room. And again, we want to shade the area to the left of that. So literally all I'm going to do is color in that left-hand side of that graph like that. So that's how I got that. Okay, so that's part A and part B. Erase that circle there so you can see it. Okay, again, part C is to provide two interpretations of that result. I'm going to provide you with 3. Okay, so one interpretation, again, they told us here that, let's suppose that that area that I just shaded was 0.3085. So what does that mean? 30.85% of the giraffe's weight is less than 2,100 pounds. Again, so that would be the percent there. The proportion, again, percent, proportion, area, all this is all the same thing. The proportion of giraffes whose weight is less than 2,100 pounds is 0.3085, or the probability that a randomly selected giraffe weighs less than 2,100 pounds is 0.3085, or again, is the probability is that it's less than 2,100 pounds is 30.85%. Okay, all of those mean the same exact thing. Okay, and that, again, question only asked you to provide 2. I gave you 3. But again, if the question only asks you for 2, you just have to do 2 out of the 3, and they'll all follow that same format. So you're either doing something like the first bullet, the second bullet, or the third bullet. And that is everything from section 7.1 now.